So now we are up to chapter 5, and in the past couple chapters, we discussed atoms and elements and their properties when they are by themselves. And so now we're going to discuss what happens to atoms when they are combined into compounds, and we'll talk about some of their properties and some of their characteristics and some of uh, their names and how they are formed and what they will form and things like that. And so in this first section, we're going to talk about this octet rule, and we're going to discuss the idea of ions. So the octet rule uses the term octet because it refers to the number 8. And so the octet rule is going to be associated with the valence shell of electrons, so the outer shell of electrons. So that's that shell of electrons that is on the outside. It is when we drew the Lewis structures of atoms in the previous chapters, it's that the ones where we're only concerned with drawing the dots. So it's also the electrons that are dealt with after when you write out the electron configurations. If you do the abbreviated version, you do the shorthand notation with the you compress the previous inner shell electrons with the previous noble gas configuration, and you just write the noble gas in brackets, and then you write the valence shell after that. So we're just concerned with those electrons in the valence shell, the outer shell. And so the most stable electron configurations for atoms is when they have a complete outer shell of electrons. And so we're going to be concerned with primarily the first two periods in the periodic table, and in that they want to have a filled outer shell of electrons. So you want to fill up the 2s and 2p, or you want to fill up the s and the p orbitals. And so you can do that by either gaining and losing electrons. And so here you have the noble gases. And we discussed in the previous chapters that noble gases don't really like to react with anything. And that's because they have a stable outer shell of electrons. They do not want to react. They don't want to gain or lose any electrons. They have a filled valence shell. The one exception to the valence electrons here, to the octet rule, as you can see, is helium, because helium only has a 1s orbital, and so you can only fit 2 electrons in that 1s orbital, and so you can only have 2 electrons in its valence shell. But once you get past that, then you can see that in there all the rest of the valence shells have 8. So outside of noble gases, all the other atoms don't have a complete valence shell. So in order to complete their valence shell, they must either gain, lose, or share valence electrons. And so we're going to talk about what types of atoms would like to gain and lose electrons, and which ones would like to share electrons. And so we can form, when they have a transfer or sharing of electrons, they form bonds, and they'll be either ionic or covalent bonds. So we'll go over the difference between those. But you can see in the picture on the right of the slide that when you have a metal and a nonmetal, there's going to be a transfer of electrons. One's going to gain, one's going to lose, and that's going to be referred to as an ionic bond. And when you have two nonmetals interacting, they're going to share electrons, and those would form covalent bonds. So metals are typically found on the left-hand side of the periodic table. And metals usually have only 1, 2, or 3 valence electrons. If you remember the first two groups, the alkaline metals and the alkaline earth metals, group 1 and group 2, they have 1 and 2 valence electrons respectively. And so in order to get to fill up their valence shell, if we are, let's just take example group 2, they want to have a filled valence shell. They want to go to octet, which is 8. So that would mean they would have to either lose 2 or gain 6. And so it's a lot easier to lose 2 electrons than it is to gain 6. And so that is why metals are more typical to form positive ions. They would rather lose valence electrons. And so there's an important thing to remember is that if you recall, electrons have a negative charge. And so if metals lose an electron, they're going to lose that negative charge. And so what will remain is a positive charge on the atoms. And so when they lose electrons, they're going to have more protons than electrons, so more positives than negatives, and so it will be positive. And so typically you'll see metals with a positive 1 or positive 2 or positive 3 charge when forming bonds. And so when they form bonds by losing electrons, they form an ionic bond. And so here we can look at sodium. Sodium is in group 1. And so to go to its a filled valence shell to get the noble gas configuration of the previous noble gas, like neon, it would have to lose 1 valence electron. It would have to lose its 3s electron. And so the 3s electron is given away, and you'll have 10 valence electrons remaining. And you'll have the noble gas you'll have the electron configuration of that of neon. And so you'll have you'll be left with a positive 1 charge, because if you lose the 1 electron, you go from 11 electrons to 10 electrons. So you have 10 negatives, but you still have 11 positive protons. So you have an excess of 1 positive charge. And so we can see the math here. So the sodium atom, you have an equal number of protons and electrons, and so you have a 0 charge with just the atom. But when you form the sodium ion, you have an excess of 1 positive charge. And so whenever we have a charge on an atom, we call that an ion. If we have an excess or a deficiency in electrons, those are called ions. And then we can do the same thing. We can look at a group 2 atom, such as magnesium. Magnesium is right next to sodium. So to have a filled outer shell of electrons, to have a noble gas electron configuration, rather than gaining 6 electrons, which is a lot of electrons, it would be much easier to just lose the 2 3s electrons. And so the magnesium atom donates its 2 valence electrons and is left with, again, 10 electrons, the electron configuration of neon. And so here you have the same math setup. In the magnesium atom, you have an equal number of protons and electrons, so you have a neutral charge, a 0 charge. But when you have the magnesium ion, you have 2 extra positive protons, so you have a positive 2 charge. So what we can do here is we can look at do these learning checks and try to figure out what is the most likely charges on some of these atoms. So the number of valence electrons in aluminum is, well, if we go to aluminum, we find aluminum in group 3A. So remember, we can use those group numbers to figure out the number of valence electrons. So since aluminum is in group 3A, it has 3 valence electrons, which is choice 3. In B, it says to acquire an octet of electrons in aluminum, it was going to require, it's a metal, so a metal would much rather lose electrons, so then we can eliminate choices 2 and 3. And it would have to donate 3 electrons in order to have a filled outer shell. And so, in C, the ionic charge of aluminum is, well, if you lose 3 valence electrons, then you're going to be left with a total of 10 electrons, right? So aluminum has an atomic number of 13. So it has 13 protons. And the atom itself would have 13 electrons. But if we lose 3 electrons, it would go from 13 to 10 electrons. So you have 13 positive protons compared to 10 negative electrons. So then you have an excess of 3 positive charges. So 3 plus is the answer for letter C. And so then the symbol for the aluminum ion is, and since we have the aluminum is symbolized by Al, and then it has a positive 3 charge. So we write it 3 positive superscript. And so that's what we can see here. And so this just kind of goes through the process of figuring out what is the likely charge for a particular ion, or the atom ion respective to the atom. And so this is the process you can go through, kind of flow through these steps. Now we can compare this to nonmetals. Nonmetals, they also want to go and have an octet. They want to have a filled outer shell of electrons, but rather than losing electrons, nonmetals want to gain electrons. Nonmetals are on the right-hand side of the periodic table, and so they are much closer to the number 8 by gaining electrons than it would have to be losing electrons. So they would, rather than losing 7, 6, or 5 electrons, is a lot easier to gain 1, 2, or 3 electrons. So in the nonmetals, you're going to gain electrons. And so when we gain electrons, we're going to be gaining negative charges. Electrons are negatively charged, so you gain negatives. And so overall, the ion becomes negative. So, and when we look at a group 17 or group 7A atom, such as chlorine, chlorine has 7 valence electrons. So to get to its octet, to get to 8, it needs to take in 1 extra electron, which would give the electron configuration that of argon. So that would give it 18 electrons. And so you can see here, chlorine is going to gain 1 electron. And so when it does that, you can see here that it's going to have 18 electrons compared to the 17 positive protons. And so it has one extra negative charge from the 1 extra electron, and so it's left with a negative 1. And so we can pretty much figure out what's going to be the most likely ionic charge based on their group numbers. So group 1, group 2, and group 3 are all metals, so they're all going to want to be positive charges, and so they're going to want to lose 1, 2, or 3 electrons respectively. For the nonmetals, you just need to subtract the the group number that it's in, so such as if it's in group 6A or 16, if you use the 6, it has 6 valence electrons, you subtract that with 8, you're left with a -2. So that's going to mean its most likely ionic charge is -2. And so you can see that here, group 1, 2, and 3 is going to have likely charges of +1, +2, and +3 respectively. Then with group numbers 5A, 6A, and 7A, they're going to have likely charges of 3 negative, 2 negative, and 1 negative respectively. And one thing that you can note here, they also have the name of the ions. And so we're going to have to determine names of chemical formulas later. But you can see here that when you see the positive charged ions, their names don't change. So if you have a lithium ion, the name of the ion is lithium. If you have a calcium ion, it's calcium. But what you can see on the other side with the negative charged ions, they have different endings to their ionic names. And so you just basically keep the first syllable and you chop off the rest of the name and add IDE as their suffix. So instead of nitrogen, you keep the first syllable, the NITR, and chop off the rest and then add IDE. So nitride. For oxygen, you chop off after the first syllable. So you keep the ox, chop off the rest, add IDE, oxide. For bromide, all right, you chop, or bromine and bromide. You keep the first syllable, the brom. Chop off the ine, and you replace it with IDE. So bromide. So we stated in chapter 3 that noble gases are very stable. They do not like to react with and interact with many other atoms because their valence shell is just so stable. And so that's the goal of all of the other atoms, is to achieve their an electron configuration to that of their nearest noble gas, whether that is to gain or lose electrons. And so when they do that, they are more stable and they are more energetically favorable. It all has to deal with the energy. And so here you just kind of has a nice little table that's useful. So just kind of shows you the group numbers. And so you see the metals, they want to lose electrons, they want to move to the left because their nearest noble gas is closer if you go in the left direction. Whereas non-metals, they're a lot closer if you move to the right direction. So you just kind of count over boxes. Like if you just count how many boxes you have to move over to get back to the previous or the nearest noble gas. So here's a learning check. It asks which group number for what's the group number for sulfur? And so we find sulfur on the periodic table, and it's going to be group 6A or group 16, which is choice 3. And so based on that, we can determine the number of valence electrons in sulfur. And so when we look at that, we find that we can just use the same group number of sulfur, which is 6. So it's going to have 6 valence electrons. Then we can figure out the charge based on that. And so it's a non-metal, so it wants to gain electrons. And it has 6 valence electrons compared to 8, which is a difference of 2. So it wants to gain 2 electrons, which is choice C. And because it gains 2 negative charges, it's going to have 18 electrons compared to its 16 protons. So it's left with a -2 charge, which is choice 2. And which we can see there. So we can also compare the size of the atoms compared to their ions. And so metals, when they lose their valence electrons, they're going to have an excess of positive charges. And so because they're going to have more positive charges compared to negative charges, those positive charges are going to pull in those negatives more. And so the metal ions are going to be smaller compared to the atoms. Nonmetals are the opposite. So nonmetals, when they gain valence electrons, there's not going to be as many positive charges in the compared to electrons. So there's not going to be as many protons pulling. Or there's going to be more electrons to be pulling toward the nucleus, and so that attraction is going to be weaker. And so nonmetals are going to be larger. And so we can compare, we can look at these pictures and we can compare the sizes, and we can see that the atoms are larger than the ions, or the ions are smaller than the atoms for the group 1 metals. But when we compare nonmetals, such as that in group 17 or group 7A, we can see that the negative ions are larger than the atoms. So here we can see, we can ask ourselves which of the following is going to be larger. And so we can compare magnesium and magnesium 2 positive. And the larger atom is going to be the magnesium. And it's because magnesium has more electrons, and the magnesium ion has less electrons. And so the magnesium ion is going to have less electrons to be attracting. And so the positive protons can put, I guess you can say, more attraction per electron. They can suck in each electron more because there's not as many electrons. Whereas if you compare number 2, sulfur and the sulfur ion should be larger because they both have the same number of protons, but there's more electrons in the sulfur ion. And so you're there's going to be, the protons have to attract more electrons, so they can't put as much attraction to each electron because there's more of them. And so the sulfur ion is going to be larger. And then in number 3, again, the bromine ion is going to be larger. Br minus is going to be larger than Br. And we can see that here. And so we want to remember that for positive ion, or for metals, the metal is going to be larger than the metal ion. But for nonmetals, the nonmetal ion is going to be larger than the nonmetal atom. And so now we can talk about ionic compounds. What happens when these metals and nonmetals get together? And so ionic compounds is when you have a compound that is made up of a positive and a negative ion. And so you have a positive ion and a negative ion, and opposites are going to attract. And when we have these opposites attracting, they form bonds, and we call that an ionic bond because we have ions forming the bond. And so when we have these ionic compounds, they're going to have new characteristics compared to the individual atoms themselves. And so they will have different properties. They'll have higher melting points and higher boiling points. And they'll be typically solid at room temperatures. So one case we can look at is sodium chloride, which is our table salt. And it's not going to be like sodium. Sodium is a metal. It's going to be shining and most silvery and characteristics of most metals. Chlorine is a gas, and so when we put these two together, they're going to be something totally different, which we get table salt. and they don't have the individual characteristics that the atoms have. They have new characteristics. So we often use ionic formulas to describe these compounds, which can give information such as what atoms and which ions are involved, how many of each of these atoms and ions are involved. And so in the ionic formula, you want to make sure that you have both a positive and negative charged ion involved in the compound. You want to make sure that overall it is neutral or zero charge, which so you have to make sure your charges are balanced. So that means that your positive charges equal the total of negative charges. And so when we write down these ionic formulas, we write down the positive first, or the metal first, and then we follow it with the non-metal, the negative. And so we can take, for example, sodium chloride, NaCl. So sodium wants to lose its one valence electron. So total positive is going to be positive 1. And chlorine wants to gain one valence electron. So it would be negative 1. So this one's rather easy to balance out. We just need one of each. And so when we write down the chemical formula, you have one Na. So you write Na first because it's the positive and it's the metal. And then you have one Cl. And so you follow it up with Cl. And you only have one of them. And so altogether you get NaCl. But now we can look at if there's not one of each. And so magnesium chloride. Magnesium wants to lose 2 valence electrons. So it's positive would be plus 2. Chlorine wants to gain only 1. And so to balance it out, you need 2 chlorines, each one gaining 1 electron. So then you would have a total of 2 lost electrons by the magnesium, by the one magnesium, and then a total of 2 electrons gained, 1 each by the 2 chlorines. And so when we have more than one of an atom, you use a subscript. So you only have one magnesium, and so if you don't have a subscript following a symbol, it's assumed to be 1. So you have magnesium, Mg, and then you have 2 chlorines. So you write Cl2, and the 2 being a subscript. And in the picture on the bottom, you can see how they made sure the charges were balanced. And so you can multiply the number of the positive ion, so which is 1 magnesium, and the 1 magnesium has a positive 2 charge, so 1 times positive 2. And you add that with the negative ion. So you have 2 chlorines, which each have a negative 1 charge. And so you end up with a positive 2 plus a negative 2, which is equal to 0, which is good because you want a balanced charge, a neutral charge. We can do the same thing here, sodium sulfide. And so here, sodium has a positive 1. It's in group 1. And sulfur is in group 6A, so it has 6 valence electrons. So sodium wants to lose 1 valence electron, and sodium wants to gain 2 valence electrons. And so in order for that to happen, we need to have 2 sodiums. So 1 sodium would be 1 positive, and then 2 sodiums would be 2 positives. And then 1 sulfur is 2 negatives. So 2 positive and 2 negative cancel each other out, balances out. So there you write Na with a subscript of 2 because you have 2 sodiums, and then just the S for sulfur. So here is just showing the another way to figure out the writing the formulas from their charges. And so you can just kind of write out, each ion individually. So in this case, you have sodium nitride. Sodium is in group 1, so it's going to have a positive 1 charge. And then nitrogen is in group 5A, so it has 5 valence electrons, so it needs 3 more, so it'll be -3. And so you need to have 3 positive charges to balance out with the 3 negatives of nitrogen. And so then that would require 3 sodium ions, each one having a positive 1 charge. Here's another example. If we had to write the ionic formula of barium 2 positive and chlorine negative. So we can write down the symbols first. So you have Ba 2 positive and Cl minus. And so to balance it out, you would have to have 2 chlorines. And so when you do that, you have Ba, and you just have 1, and then Cl2, because you have 2 chlorines. And so here, it's just going to ask us to solve for the correct formula. So in A, it's sodium plus and sulfur 2 minus. And so we already did this one previously, but we can see that we have 1 positive and 2 negatives. So we need to get another positive charge. So that means we require 2 sodiums. So that would require, so that would give us the chemical formula Na2S. In B, we see aluminum 3 positive and chlorine negative. So we have 3 positives, only 1 negative. So we need to get 2 more negatives, which give us 3. So that means we need 3 chlorines. And so if we have 1 aluminum and 3 chlorines, that would give us AlCl3, which is choice 1. And then C, a little bit trickier. And so in C, we pretty much have to find the common denominator, common factor. And so the lowest common factor of 2 and 3 is going to be 6. So in this case, we would have to figure out what we would have to do to 2 to get to 6. And so we would need 3 of them. So we would need to multiply 3 times 2. And so magnesium, we'd need 3 magnesiums. Then to get the 3 of nitrogen, 3 negative, to be a 6, we have to multiply by 2. So you need 2 nitrogens. And so that would give us magnesium 3, nitrogen 2. And there's another way that we'll go over later on in this PowerPoint that I added in that may be easier to do. And so here is just kind of showing you the math behind it and showing you the balancing of charges, in which we pretty much just went over verbally. And so this can kind of maybe help you to see it visually. And so in this part of the chapter, we're going to come up with a systematic method of coming up with names and formulas for ionic compounds. And so we went over this. We went over, the likely charges of these ions based upon their group numbers. And so these are the ones you kind of want to remember. There's nothing that's going to be given, so you'll have to remember these, or at least remember the way it was figured out anyway. And so here it just kind of goes over the names of the compounds. So when we have sodium and fluorine, remember we said that sodium keeps its name. So the metal ions do not change their names. It's always going to remain the way it is written in the periodic table. So Na is always going to be sodium, magnesium is going to be magnesium, aluminum is going to be aluminum. So the metals don't change. The only ones that really can change is the nonmetals. And so when they are in compounds, you want to what you have to do is nonmetals, you keep the first syllable and you chop off the rest, and then you add the suffix ide, IDE. So fluorine becomes fluoride, bromine becomes bromide, oxygen becomes oxide. And so when they are in compounds, just like how in chemical formulas we wrote down the metal ion first, we also say the metal ion first. So in NaF, it's going to be sodium fluoride. In magnesium and bromine, it's going to be magnesium bromide. In aluminum oxygen, it's going to be aluminum oxide. And so here we can just kind of go over the check of, what would we name these ions. So remember, metals, they're going to keep their name. They're not going to change. So Ba2 plus, it's going to be still barium is barium. Al3 plus, that's aluminum, and aluminum is going to stay aluminum. K is potassium. Potassium is going to, no matter atom or ion, it's going to stay potassium. All right, now for nitrogen, N3 minus, all right, we are going to keep the first syllable. So we keep the NITR, and then we chop off the rest. We chop off the ogen and replace it with IDE. So it would be nitride. Oxygen, you chop off the gen part of it, or the igen part of it, and then you replace it with IDE. So oxide, you keep that first syllable. Fluorine becomes fluoride. Phosphorus, phosphide. Sulfur, sulfide. And chlorine, chloride. So you keep that first syllable, chop off the rest, replace it with IDE, ide. All right, and so we see there. So metals stay the same, non-metals, first syllable, ide. So here's just a flow chart of the way to come up with ionic compounds names. So it's pretty much just putting together everything we have gone over in the previous slides. What you want to do is you want to first identify the metals and the nonmetals. The metal is going to be the positive, and the positive ion is what we call a cation. Then you want to identify the nonmetal. The nonmetal is going to be negative, and what we call a negative ion is an anion. And so you write down the cation first, and then you write down the anion. But for the anion, you want to remember that you only keep the first syllable, you chop off the rest, and then you add the IDE. So you keep first syllable, ide. Then you write down the cation first and the anion second. So here's just some examples. All right, we have Na and Cl. Na is in group 1, it's the metal. It's going to form positive charges. It's going to be the cation. Chlorine is found on the right side of the periodic table. It's non-metal. It's going to want to be negative ions. It's the anion. So for the metal, the cation, the positive, we just keep the same name. So sodium remains sodium. For chlorine is the non-metals, the negative, the anion. So we keep the first syllable, the chlor, drop off the rest, then add IDE, ide. So sodium goes first, chloride is written second. Potassium and sulfur. Potassium is the positive. Potassium is the metal. Potassium is going to be the cation. And so potassium is going to remain potassium. Sulfur. Sulfur is the non-metal, the negative, the anion. So sulfur, you're going to keep the first syllable, the sulf. You chop off the rest and you add IDE, so sulfide. It's going to be the cation first, potassium, then the anion second, sulfide. And then the rest are following the same steps. So you follow that same order of events and then you will get those same answers. So here's a learning check to make sure we understand. So we have calcium and we have oxygen. So calcium is the metal. Potassium is going to want to lose electrons. Potassium is going to become positive charge. Potassium is going to be the cation. Oxygen is on the right side of the periodic table. It's a nonmetal. It wants to gain electrons. It wants to become a negative ion. It wants to be the anion. So calcium is the cation. It's going to keep its calcium name. Oxygen is the anion. You keep the first syllable. Ox, chop off the rest, add IDE, oxide. The positive is written first, calcium, negative second, oxide. So calcium oxide. We have potassium, we have bromine. It's going to become potassium bromide. Aluminum and oxygen. Aluminum, written first, oxide. Aluminum oxide. And then the last one, magnesium is the metal. Magnesium first, chloride second. Chlorine is the negative ion, so magnesium chloride. And so that's how it's written here. Here, we can do a learning check of figuring out the formulas and names of these compounds. So we can balance out the charges and then come up with their names. So sodium is +1 and bromine's -1. So those +1, -1 balance out. So we end up with NaBr. Sodium's the plus, sodium stays sodium. Bromine's the negative, bromide. All right, then staying with sodium. All right, sodium's +1, sulfur's -2. You need two positives to balance out the two negatives. So you need 2 sodiums, 1 sulfur, so Na2S. And I'm just going to go to the next slide so it's better seen. And then we have sodium being the positive. Sodium is written first, and then sulfide. Then for sodium and nitrogen, sodium is +1, nitrogen -3. So we need 3 positives to balance out the 3 negatives. So it'll be Na3N. And then sodium is first, sodium is positive, sodium is first, sodium stays the same, sodium. Nitrogen's negative, nitrogen, you keep the first syllable, add IDE, so sodium nitride. And the same thing here is done with aluminum. So you need, you have aluminum with the +3, so you need 3 negatives, so you need 3 bromines, so AlBr3. And aluminum is positive, aluminum is written aluminum. Bromine's negative, keep the first syllable, add IDE, bromide, aluminum bromide. Aluminum and sulfur. Aluminum, this one's a little tricky. You need to find the common factor, again, which is 6. So in order to get the aluminum 3 to 6, you have to multiply by 2. For sulfur to become 6, you need to multiply by 3. So it's Al2S3. And then that becomes aluminum is positive, aluminum is aluminum, sulfur is the negative. Sulfur, you have to keep the first syllable and add IDE, aluminum sulfide. And then aluminum and nitrogen, aluminum is +3, nitrogen is -3. They are balanced, so it's just Aln. Aluminum is the positive, aluminum stays the same, aluminum. Nitrogen is the negative, nitrogen you keep the first syllable and then add IDE, aluminum nitride. Transition metals are still metals, and so the metals will lose electrons and form positive charges. But with the transition metals, typically you're going to be given what the charge is going to be, or you can figure it out from chemical formulas or from the chemical names. So so we'll go through the steps on how to figure out these transition metal charges. And that's what it really means by transition. It's transitioning because most of them have more than one positive charge. It can transition between different charges. And so with the transition metals, often with transition metals, if it's written in the name, it's going to be followed with a Roman numeral. And that Roman numeral is going to be its ionic charge. So in that chart on the right, you can see chromium can be either +2 or +3. So when you write out the name of the ion, because it's a metal, it still says the same name. So you still write it as chromium. And then you have a Roman numeral followed after it. So if it's chromium +2, then it's chromium 2. If it's chromium +3, it's chromium 3. And then same thing with all the rest of these transition metals. So the ionic charge will be identified with a Roman numeral following after the name of the metal. And so it follows much of the same naming rules as in the previous flowchart we saw. The only thing here is that we just need to include the Roman numeral after the metal's name. And so here we see a chart of doing exactly that. If we have iron chloride, Fe is iron, Fe is a +2 charge, because here we can see that chlorine has to have a -1 charge. And chlorine, we see it's written as Cl2. That means there's 2 chlorines. Iron, or the Fe, must be positive. And to balance out the 2 negative charges, you need 2 positive charges. So iron, in this case, must be +2. So in writing that, we'd write iron with the Roman numeral 2, and then chloride. We can take another one. So if we do copper and phosphorus. Phosphorus is in group 5A, which means it has 5 valence electrons, which it needs 3 more. So phosphorus is going to be a -3 charge. Copper, then, to balance out 3 positives, if we see that we already have 3 coppers, then if each one is a positive, then it would balance out the 3 negative. So 3 positive and 3 negative. So copper and phosphorus is going to be a +1 charge. So we would write it as copper, Roman numeral 1, phosphide. So this chart is showing the same flow chart as before. So just follow these steps in naming the ionic compounds if they have more than one possible charge to the metal. And so in step, if we are trying to name FeCl2, as we did in the previous case, it's kind of showing how it's done. So we know we have an iron ion, and we know we have chlorine ions. We know we have 2 chlorine ions. And because chlorine is in group 7A, we know that each of those chlorines needs 1 extra electron. If it adds an electron, it's going to become a -1 charge. So we have 2 chlorines, or we have 2 negative charges from the chlorines. In order for that to balance out, balance out the charges to become 0, then we need 2 positives, which would have to come from the iron. And so because we only have 1 iron in the chemical formula, then the iron must be a +2 charge. And so in writing out the cation's name, we would write iron and then use the symbol, the Roman numeral 2, following after iron. Then with the anion, we have chlorine, so we keep the first syllable, chlor, and then add it with IDE, chloride. And so we write the cation, or the metal first, iron 2, and then end it with the anion, the negative, the nonmetal, the chloride. So iron 2 chloride. So this is a good example in showing when it's a little bit more difficult in balancing out the charges. And so this one we have to find the common factor. All right, and so here we have 3 oxygens and we have 2 chromiums, and the chromium is the one that we're trying to investigate and figure out the charge on. So we know oxygen is in group 6A, so it has 6 valence electrons, so each one needs 2 more electrons, so each oxygen is going to become a negative 2 charge. And we know we have 3 of them. So we have a total of 3 times 2 negative, which would be a total of negative 6 from the oxygen. And we have 2 chromiums, and which have to be positive. So if we want our charges to balance out, we need a total of 6 positives. And so if we divide 6 by 2, we get 3. So chromium must be a positive 3 charge. And if it's a positive 3 charge, we write it as chromium, Roman numeral 3. Then with the anion, oxygen, we keep the ox and add it with IDE, oxide. So chromium 3 oxide. So here's a good learning check, trying to figure out which is the correct name. So we have, basically we need to figure out what the charge is on the iron. And so sulfur is in the 6A group, which means that each sulfur is a negative 2 charge. And we have 3 of them, so that would be a total of negative 6 from the sulfur. That would mean we need a total of positive 6 from the iron. So we have to divide our 6 from the sulfur by 2, since we have 2 irons, which gives us 3. So iron must be positive 3. So it would be iron 3 sulfide. In B, we have copper and oxygen. So oxygen in group 6A. Oxygen must be a 2 negative charge. And so we only have 1 copper, so to balance out the 2 negative, we need 2 positive. So it must be copper 2 oxide. And that's what we see here. So remember to balance out our charges and then come up with your names. And don't forget to include the Roman numerals. Now we can kind of go in reverse and come up with writing out the formulas from the names. So if we have potassium sulfide, we have to use our periodic table. So potassium's in group 1. Group 1 has a positive 1 charge. Sulfide refers to sulfur. It's in group 6A, which would mean that it has 6 valence electrons, which needs 2 more, so it wants to become a negative 2. So we have one positive and 2 negatives. So in order for that to balance out, we need another positive, so we need 2 potassiums. So we have 2 potassiums, we get positive 2, we have 1 sulfur, negative 2, and balance that out. And so we write that with K for potassium, subscript 2, since we have 2 of them, and 1 sulfur, so 1 S. We have the S written after it. We don't need to include the 1 because if there's no subscript, then it's assumed to be 1, so K2S. Here's the other method that I added in that I found very helpful. And so most people call this the crisscross method. And so you basically follow the same initial steps. You have to identify the cation and anion, so just identify the metal and the nonmetal. So potassium is going to be K, and it wants to be positive 1 charge because it's in group 1. Sulfur is a nonmetal, so it wants to be the anion, still wants to be 2 negative. And so how you can do this is just write their charges below their symbols. And then you just crisscross. You use the absolute value of their charges as the other atoms or the other ions subscripts. So the 2 from the sulfur is going to be the subscript for the potassium. So K2. And then the 1 from the potassium is going to be the subscript of the S. So S1. So K2S1 or K2S. We do that same thing here, the original method, the way the book has it, with iron 3 chloride, iron 3, we have that Roman numeral 3, which symbolizes the 3 charge. And we have chlorine, chlorine's in group 7A, so it wants to be a -1 charge. And so we have 3 positives, then we need 3 negatives. And so then we'll need to balance that out. So we have to have 3 chlorines. So we would have Fe, then Cl3. Here, showing the crisscross method, if we know that iron is the metal, it's going to be +3. Chlorine is the negative, so it's going to be -1 because it's in group 7A. So then the 1 of the chlorine becomes the subscript of the Fe, of the iron, and the 3 of the iron becomes the subscript of the chlorine, the Cl. So it would be FeCl3. And so here we can just go over some other examples. So copper 1 nitride. And so we'll just kind of use the crisscross method. So copper is +1, nitrogen is -3 because it's in group 5A, so it needs to go and gain 3 valence electrons. So the 3 of nitrogen is going to become the subscript of copper, and the 1 of copper is going to become the subscript of nitrogen, so it's going to be copper 3N. Lead 4 oxide, lead is with the Roman numeral 4. So it's going to be +4, and oxide is in group 6A, so it wants to be a -2 charge. So then we can use the crisscross method. So the 4 of lead, Pb, goes to oxygen, and then the 2 of oxygen goes to the subscript of lead. So that would give us Pb 2O4. But in writing out chemical formulas, we need to write out the most simplest form. So we always need to divide by the largest common denominator. So because Pb2O4 is not technically wrong, but it's not technically right either because it's not its most simplest form. We need to divide that whole thing by 2. And so when we divide Pb2O4 by 2, we get PbO2, which is choice 1. Okay, so I don't know if we ran into any other examples that mention that, so you'll have to remember that you want the chemical formulas to be the most simplest term. So if they have a common denominator, they must be divided by that largest common denominator. We're going to mention polyatomics solely based on seeing them in some of the chemicals that we may encounter in labs. I'm not going to really go and ask you questions on exams or anything like that, but I just want you to be aware of these polyatomics. So these prefix poly just means many or more than one, and atomic just deals with atoms. So these are a group of atoms that are together as an ion. And so these are just some examples. NH4 plus is ammonium. NO3 minus is nitrate. You probably have even heard of these things before. You probably have heard of hydroxides and phosphates and carbonates. And so these deal with compounds that have polyatomic ions in them. There's a systematic way of coming up with their names for the polyatomics, whether it is ending in ate or ite and anything like that. But we are, I'm not going to quiz you or expect you to do any of that on any of the tests. So we're just going to skip over this. But these are just some of the most common polyatomics. And so I just want you to be familiar with some of these names as far as hydroxide, ammonium, nitrate, carbonate, sulfate, phosphate. I think those are the most popular ones. To a lesser extent, acetate and cyanide, and nitrite. But the rest of them we won't really go over in the class. But these are just some common compounds that have potassium, polyatomic ions in them, and some of their uses. But that's we'll just skip over this as well. So there's again a systematic way of coming up with the names of chemical compounds using polyatomic ions. And so we basically just want to keep together the groupings of the polyatomics. All right, so you're not going to separate out the nitrogen and the oxygens and nitrate. They get grouped together in one name. So I guess that you just have to familiarize yourself with some of those symbols and recognize that those are polyatomic ions. And so if we had to match the correct names of these formulas, so if we have MgS, right, that's not a polyatomic, so that follows the normal set of rules that we have had. So that's going to be magnesium, as it's always written first. Magnesium is the metal, and then sulfide. So that's going to be 3. Then with magnesium, I would skip down to the third one, MgSO4. And because SO4 is the most common one, SO4 is sulfate. So it would be magnesium sulfate. And then the one less oxygen is going to be sulfite. So it's going to be in order. MgS is going to be choice 3. Then MgSO3 is going to be choice 1. And MgSO4 is choice 2. Then we have we can start off with the one that we're probably most familiar with, CaCl2, and so that's going to be calcium, and then it's going to be chloride, and so that would be choice 3 for the middle one, and that just follows our normal set of rules. And then the ClO3 is chlorate, and ClO2 is chlorite, and so in order it's going to go from top to bottom is going to be 1, 3, then 2. Coming up with the chemical names, all right, we have MgNO3. So NO3 is nitrate, so it's going to be magnesium nitrate. ClO3 is a polyatomic for chlorate, and so chlorate has a -1 charge. So if we have a -1 charge on one chlorate, we have 2 of them, that's a total of -2. And if we have a -2 from the chlorate, we need a +2 from the one copper, so copper must be +2. So it would be copper 2 chlorate. In choice C, it's our normal set of rules that don't deal with polyatomics, so it's just going to be, but we have to figure out the Roman numeral. And so oxygen is -2, and we have 2 of them, so that's going to be a total of -4. And so then lead needs to become a +4. All right, so it's going to be lead 4 oxide. SO4 is sulfate. We have 3 of them. So we have a total, and sulfate is a -2 charge. So it's going to be a total of -6 from the sulfates. And iron we have it's going to be we need a positive 6 from the irons. We have 2 of them. So 6 divided by 2 is 3. So it's going to be iron 3 sulfate. And then PO3 is phosphite. So it's just going to be barium phosphite. And so, like I said, with these polyatomics, I just want you to be able to recognize what polyatomics are. Went through these examples. I'm not going to really expect you to go through and solve for chemical formulas and names from the polyatomics. But again, this is just going in reverse. So coming up with the chemical, writing the formulas out. And so just remember to balance out the charges. When we have these polyatomics in parentheses, the subscript outside the parentheses goes with the whole polyatomic. So in this case, if we have aluminum nitrate, nitrate NO3 has a -1 charge. Aluminum has a +3 charge. So if we have a +3 for the aluminum, then we need -3 from the nitrates. But if only one nitrate has one negative, then we need 3 nitrates. So the Al parentheses NO3 in parentheses 3, choice 3. And so copper 2 nitrate, again, copper is +2, nitrate is -1. So we need 2 nitrates to balance the 2 negatives to balance out 2 positives. So it would be Cu parentheses NO3 parentheses 2. Iron 3 oxide, much the same. Hydroxide is a -1 charge. The iron has a +3 charge, so you need 3 hydroxide. So remember to use your parentheses. So it would be iron Fe parentheses OH in parentheses 3. And so then the tin hydroxide is done much the same. So writing out the chemical formulas for each of these. Again, I'm not going to ask you to do this, so we'll just skip over this slide. You can check yourself if you want to, but we'll just start with the polyatomics. But this is a nice little flow chart and figuring out how to name ionic compounds for ionic compounds. And so just you have to figure out in the compound what is the metal and what's the non-metal. Figure out if the metal is a transition metal or not. Then with the non-metals, look at it and see if it's if the polyatomic or not. Most of our cases are not going to be. So another learning check coming up with formula name, chemical names. So we have Ca3PO42. PO4 is phosphate, and so it's going to be potassium phosphate. FeBr3. This one, so here we can see Fe is a transition metal, so we need to figure out the charge. So bromine is a 7A atom, and so it wants to form a -1 ion, so you have 3 of them, so you have a total of 3 negatives. And then iron, then you'll have 1 of them, so you need a +3 from iron, and so iron must be +3, so it'd be iron 3 bromide. And so that's how these are done. And so you can try them out and check yourself using this answer sheet. Going in reverse, coming up the chemical formulas from the names. So calcium nitrate, nitrate is NO3. It's a -1 charge. Calcium is a group 2A element. It wants to be +2. So if you have +2 from calcium, -1 from nitrate, you need 2 negatives. So you need 2 nitrates. So calcium parentheses NO3 and parentheses 2. Because you need 2 nitrates. And you need the parentheses to make sure that it says 2 nitrates. Iron 2 hydroxide, hydroxide OH, negative. It's -1 charge. Iron here is +2, so you need 2 negatives, so you need 2 hydroxides. And so it would be Fe parentheses OH and parentheses 2. And then you can try the rest out and check your answers and see if you get the same there. And so just follow sets of rules. So now it brings us to covalent compounds. All right, and so these have some different sets of rules. So we had the ionic compounds, they have their set of rules. Now we have covalent compounds, they have their own set of rules. All right, and so covalent bonds, they are formed when atoms share electrons. So rather than forming ions, rather than one part gaining electrons, one part losing electrons, these share them to complete their octets. And these are formed from 2 nonmetals. So covalence was metals with nonmetals. Covalence is going to be 2 nonmetals. So they just go with the simplest covalent molecule is H2 because to fill up the outer valence shell of hydrogen, hydrogen's valence shell is the 1s, and you can only have 2 electrons in the 1s shell. Each hydrogen has 1 electron, so each hydrogen needs 1 more. So what each hydrogen does is it moves close enough to where the electrons are shared. And so when they are shared, then hydrogen has 2 valence electrons and the other hydrogen has 2 valence electrons, and so they share a covalent bond by sharing electrons. And we kind of see that here. So as they get closer together, they become attracted because their electrons are attracted to the other atom's nucleus. And so that's what keeps them together, is the attractions of the electrons to the other atom's nucleus. So here we see another example, fluorine. Fluorine is a group 7a electron. It needs 1 more electron each. So fluorine is going to want to share 1 valence electron with the other fluorine, and the other one's going to share it back. And so when each fluorine shares 1 electron, then they both complete their octet. And so you kind of see that with these Lewis structures here. You had the 3 lone pair electrons on each, and then the 1 lone electron, unpaired electron. And when those unpaired electrons go in between and get close enough, they can be shared. And when we write out their Lewis structures, when they share an electron, we can draw that with a line, symbolizing the covalent bond. So certain elements form diatomic elements. So the prefix di means 2, and then we call these specific atoms that we have hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. They all form diatomic covalent molecules. They is stable. It's energetically stable for them to form covalent bonds with each other, and that's how they are found in the natural environment. So when we say we are breathing in oxygen, we're not just breathing in the atom oxygen, we're breathing in O2, because that's the way it is found in nature. That is most energetically favorable and is most stable. So if we come up with the names of these diatomic molecules, so these diatomic molecules, their molecular names do not change. Hydrogen stays hydrogen, nitrogen stays nitrogen, chlorine stays chlorine, oxygen stays oxygen, iodine stays iodine. So diatomic molecules do not change their names from their atomic names. And so that's what we see in this solution here. Carbon is one of the more interesting elements because that is the fundamental element on which our life on Earth is based upon is carbon. We are all carbon-based organisms. And so carbon likes and prefers to form 4 covalent bonds. And so in the case of methane, well, carbon again is in group 4A, so it has 4 valence electrons. They are all unpaired electrons. And so because they're all unpaired, they're readily available for forming bonds. And so methane is CH4, it's a natural gas, and so each hydrogen wants 1 more electron to fill its valence shell. And the carbon needs 4. And so in order to become a stable molecule, carbon requires 4 hydrogens to be bonded with. And so when it does that, carbon then would have a complete octet of 8 electrons. So if each hydrogen shares 1 electron with carbon, it adds 4 more to its valence shell. So 4 goes to 8. And then each hydrogen gets to share 1 electron with the carbon. So hydrogen goes from 1 to 2. And so they are both fill up their outer valence shell of electrons. We see the same thing here with nitrogen. Nitrogen in group 5A, it wants 3 more valence electrons in its valence shell. We write out its Lewis structure or electron dot structure. We have one lone pair of electrons, and then 3 unpaired electrons. So it needs 3 more electrons to fill its valence shell, and so it would form 3 bonds with hydrogens. So it needs 3 different hydrogens. So when it forms these bonds, each hydrogen shares 1 electron. There's 3 of them, so that brings 3 more electrons to nitrogen, which brings 5 to 8. Then in response, hydrogen gets to share an electron back, and it goes from 1 to 2. And so we can see how the electrons are shared in the pictures below. And then we can see we can symbolize those shared electrons with those lines. So we draw a line to symbolize the bond. And then we call those electrons that are not involved in bonding lone pair electrons. And so here you can kind of just see how many covalent bonds these atoms prefer to make. And so again, it's largely based on their groups and how many electrons they need to complete their octet. So hydrogen needs 1 to fill its 1s orbital from 1 to 2. Boron is an oddity. It's only going to make 3 bonds. So boron is an exception to the octet rule, and it's unlike most other covalent molecules or atoms involving covalent bonds. But the rest follow suit. So in group 4, it needs 4 electrons to fill its octet, and so it's going to form 4 covalent bonds. Nitrogens, group 5A, they need 3 more electrons to fill up their octet, their valence shell, so they form 3 bonds. Group 6A, 2 bonds. Group 7A, 1 bond. And so we can see these electron dot structures of these covalent compounds. So CH4, it's going to form 4 bonds, and there will be no lone pair electrons. So there's going to be 4 covalent bonds with hydrogens. NH3 is going to be left with 1 lone pair electrons, and so you form 3 bonds with hydrogen and 1 lone pair. And then oxygen and hydrogen form H2O, and so they form 2 covalent bonds with hydrogen and oxygen, and then you're left with 2 lone pair electrons. So this is just a nice little flow chart on how to write out the electron dot formulas. You want to figure out the arrangement of the atoms. So you want to figure out which atom should be the central atom, and typically the central atom is going to be the atom that requires the most bonds to complete its octet. So comparing carbon to oxygen, carbon needs 4 bonds, oxygen needs 2. So carbon is going to be the central atom. If we compare nitrogen and oxygen, nitrogen needs 3 bonds, oxygen needs 2. So nitrogen becomes the central atom. Then we can determine the total number of valence electrons. So that's based on their group numbers. Then we determine we bond the atoms together from the outer atoms to the central atom. And we start off with just one pairing. Then we can put the rest of the electrons as lone pairs to complete octets. So again, determine the arrangement of the atoms, figure out which one's the central atom, whichever one requires more bonds is the central atom. Determine the number of valence electrons. Attach the bonds to the central atom with a pair of electrons. Place the rest to fill octets. And if the octet is not complete by doing that, form multiple bonds. And you do that by just moving the lone pair electrons and putting that as an extra bond. So to practice through this figuring out the electron dot formulas, we'll start off with the CH4, the methane. And so first thing we want to do is figure out the atom arrangement. So because carbon requires 4 bonds in order to reach an octet, then and compared to hydrogen's only 1, then carbon is going to be its central atom with the hydrogens arranged around it. And so the total number of valence electrons, you have 4 from carbon and 1 from each hydrogen, and so that brings it to a total of 8. So what we do is we put carbon in the middle, and then we put each hydrogen around the carbon, and then putting in 2 electrons for each bond. And so since there's 4 hydrogens and 4 hydrogen-carbon bonds, that's 8 electrons, and so that leaves a remainder of 0 electrons. And so each of those pairs of electrons are shared between carbon and hydrogen, and so those form a bond. And so we symbolize those bonds with a line. And so we can just write carbon with 4 hydrogens around it connecting with a bond or a line. We can have single bonds in which we have 1 pair of electrons shared, a double bond in which 2 pairs of electrons are shared, so that's a total of 4 electrons, and a triple bond where 3 pairs of electrons are shared, or a total of 6 electrons. And so if we look in the case of CS2, all right, carbon requires 4 bonds, sulfur requires 2 bonds, and so carbon is then the central atom. Carbon has 4 valence electrons, sulfur has 6, so that brings us a total of 16 valence electrons. So we arrange the atoms as such. We see carbon in the middle. We put 2 pairs of electrons in between them. And so we have, that's a total of 4 electrons. So it's 16 minus 4, which is 12 remaining. And so then we just put the rest as lone pairs. So arbitrarily, we just put them around sulfur. But we can see here that would satisfy sulfur's octet, each of them, but carbon has an insufficient number of electrons. Carbon will only have 4. So we need to then do step 5, in which we have to bring a lone pair of electrons from each sulfur to add another bond between the carbon and sulfurs, and that would make them double bonds. And so there we can see that we would have 4 electrons between each carbon and the sulfur, and that would be a double bond. And so we draw double bonds with two lines connecting the two atoms. And so then that would satisfy the octet for each element. So there would be a total of 8 electrons around the carbon, each bond having 2 electrons. And so since carbon would have 4 bonds, that'd be a total of 8 electrons. Then each sulfur has 2 bonds, and so that's a total of 4 electrons. And then 2 lone pairs. So that would be our 2 unpaired 2 lone pair electrons, and so that would be a total of 4 as well. So 4 in bonds, 4 lone pairs, which is a total of 8. So it fills its octet as well. Here we can see in the case of a nitrogen molecule forming, we have a triple bond. And so nitrogen is a diatomic molecule, N2, and each nitrogen has 5 valence electrons, and so it requires 3 additional electrons, so it's going to share 3 electrons to fill up its octet. And so because it's only 2 nitrogens and each nitrogen needs 3 more electrons, each nitrogen is going to share 3 electrons. So you're going to have 3 electrons shared between each nitrogen, which is a sharing of 6 total electrons, and that's 3 separate bonds, each bond having 2 shared electrons. And so we form a triple bond, and you can see the electron dot structures drawn from atoms to showing the electrons being shared as dots, and then to showing them the bonds drawn as lines. So now this brings us to naming and writing covalent formulas. And so this is a little bit different from ionic bonds and ionic formulas. So they have some similar rules, but some different rules as well. So in covalent bonds, we actually use prefixes to symbolize the number of each atom involved in the molecule or the compound. Whereas in ionic bonds, we never used any prefixes. You figured out how many of each atom you had based on their charges. And here in covalent bonds, the names of the formulas includes how many of each atom you have. And so here you can see from NO2, anode, NO2, N2O, and so on and so forth, they use prefixes to symbolize how many of each atom you have. And so NO is just nitrogen oxide. And so there's no prefixes, and so we then can say that there's only one of each of the atoms. Whereas NO2, we have 2 oxygens, and the prefix that we use for 2 is di, so nitrogen dioxide. In N2O, we have 2 nitrogens, so we call that dinitrogen oxide. In N2O4, we have 2 nitrogens, so it's dinitrogen O4 tetraoxide. And N2O5, we have 2 nitrogen, dinitrogen, and 5 oxygens, pentaoxide. So here is just showing the flow chart on what's going to be done in naming these compounds. And so you name the first nonmetal with its elemental name, and then the second nonmetal, you're going to use the first syllable, then you're going to remove the rest, and then add IDE. And then lastly, you can add prefixes to indicate the number of each atom, or the numbers used in the subscripts. So In step 1, you name the first nonmetal by its elemental name, second nonmetal with IDE ending, then the prefixes. And so here's a nice little table that shows you the prefixes used. Every once in a while we use mono, um, but that is only in certain cases. Not many times do we use mono. Just for certain ones, some typical compounds, like carbon monoxide is one example, but often it's omitted. The prefix for 2 is di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, and 10 deca. And so if we have the compound SO3, if we had to figure out the name, the first one that's written is S, so that is sulfur, and so we use just the name sulfur, and then oxygen is written second, and so it's going to be oxide, and then because we have 3 oxygens, then we use the prefix tri for 3, so trioxide. And we don't typically use the mono for 1, so we're just going to use sulfur trioxide. We have P4S3. The first one written is phosphorus, so it's going to be P for phosphorus. The second one is S, so S is sulfur, but we have to replace the ending with I, so it's going to be sulfide. We have 4 phosphorus, and we have 3 sulfur. So 4 is tetra, 3 is tri. So it's tetra phosphorus, trisulfide. And so these are just a table of some common covalent compounds, what their uses are for, and things like that. But it's a nice little thing that kind of shows you the formula and the names, and you can see those trends that we have discussed. So the flow chart here, a little bit more simple. First, with the first nonmetal, the second nonmetal. So for the first nonmetal, make sure you have the prefix matching the subscript. And then with the second nonmetal, make sure you have the prefix, then the name of the first syllable, and then ending it with IDE. So here's just a quick check on what we've been going over. So the first one written is Si, and so that's the symbol for silicon. So we write silicon first, and then we have 4Cl, so that's chlorine. And so because it's the second one, we have to add it with chloride, and we have 4 of them, which is tetra. So it's going to be silicon tetrachloride. For B, we have P, which is phosphorus, and we have 2 of them, so it's going to be diphosphorus. And then we have oxygen, so it's going to be oxide, and we have 5 of them, so it's going to be pentaoxide. So we have diphosphorus pentoxide. And then C, we have 2 Cl's, which is dichlorine, and then we have 7 oxygens, which is heptoxide. So it's dichlorine heptoxide. And so you have that there. If we have to write out the names for these formulas, we have CO, so that would be carbon oxide, and this is also mostly referred to as carbon monoxide. Then we have CO2. So CO2, we have C for carbon, 2 oxygens, so dioxide, so carbon dioxide. PCl3, we have P for phosphorus, we have Cl for chlorine. We have to replace that with chloride. We have 3 of them, so it's trichloride. So phosphorus trichloride. CCl4, C for carbon, Cl for chlorine, so we replace that with chloride. We have 4 Cl, so tetrachloride, so carbon tetrachloride. And then N2O, we have nitrogen, we have 2 of them, so it's dinitrogen, then oxide. And so that's what's written there, and that's how you'd write it out. So when we are trying to write the formulas for covalent compounds, then we write the symbols in the order that the name is written, and then we use the prefixes and use them as their subscript. And so that's what is done here. So we have carbon disulfide. So the symbol for carbon is C. And the symbol for sulfur is S. So we write CS. We have no prefix for carbon, so there's no subscript for carbon. But we have a prefix for disulfide, and so we have to use di, which is 2, so that's going to be disulfide. So here in our learning check, we have to do much the same. So we have to come up with the correct chemical formulas. So in A, we have phosphorus pentachloride. So phosphorus is symbolized by P, and chloride is Cl, and we have the prefix penta, which symbolizes 5. So it'd be PCl5. For B, we have dinitrogen trioxide. So nitrogen is N, oxide is O. So dinitrogen is 2, so that's N2. And then trioxide, that's 3, so that'd be O3, so N2O3. Sulfur hexafluoride, we use the symbol S for sulfur and Fl for fluoride, and then the prefix we have is hexa, which is 6, so it'd be SF6. And there we go. And so we go first to figure out the symbols, then we figure out the subscripts by their prefixes. So in this part, it's kind of combined everything, and this is probably more applicable to what you would have to do in the on a quiz or something, because I'm not going to be telling you if it's ionic or covalent, and so you will have to determine that. And then based upon that, then you can come up with its correct name. So in A, it's SO2, and S is a nonmetal, and O is a nonmetal, so we have 2 nonmetals, and so that would be a covalent bond. And so that's how you should be starting, coming up with the correct names or formulas is based upon their first thing is to figure out their ionic or covalent. So A is covalent, and 2 nonmetals. So we write sulfur for S, oxygen for 2, so it's going to be sulfur oxide, and then we have 2 oxygens, so we have to use a prefix because it's covalent, so it's going to be sulfur dioxide. For part B, we have barium, which is a metal, and chlorine, which is a nonmetal, so that's going to be an ionic bond. And so we'll just simply say barium chloride, so we don't have to worry about anything else from there. And because barium is a non-transition metal, we don't have to worry about symbols like that. Part C, we have it's ammonium and phosphates, and so that's an ionic bond, and so we don't have to worry about prefixes. We don't have to worry, and so there we just have to figure out it's ammonium phosphate. So we just put together the polyatomic names. Cu2CO3, so that is a metal with a polyatomic, so that's ionic. Carbonate has a positive 2 charge, and so that would mean that we need a total of, carbonate has a negative 2 charge, and so we need a positive 2 charge coming from the copper. We have 2 coppers, and so that means each copper is a positive 1. So it would be copper 1 carbonate. And then in part E, we have nitrogen and oxygen, both of which are nonmetals, and so that would mean that we have a covalent bond. And so we have to use prefixes. So here we have nitrogen and 2 of them, so dinitrogen, and we have 4 oxygens, so tetraoxide. And so we see that here. So you have to figure out if it's ionic covalent, then you can go on with the naming. So in this learning check, you do much of the same. We'll skip A because it has a polyatomic, so we'll just go to B through D. So first thing you want to do, is it ionic or covalent? Then go on with the naming. So we have a metal with a nonmetal, iron with bromine, so that's got to be ionic. So we don't have to worry about prefixes or anything. The only thing here, we have a transition metal, so we need to figure out the transition state or the charge. Bromine is 7A, so bromine is a -1 charge. We have 3 of them. So that's a -3 from bromine. So that means we need a +3 from iron. Iron is only one of them, so it's got to be +3. So it'll be iron 3 bromide. In C, we have sulfur and we have chlorine. Sulfur and chlorine are both nonmetals, so covalent bonds. So it'll be sulfur and 2 chlorine, so it'll be sulfur dichloride. And D, we have chlorine, we have oxygen, 2 nonmetals. So that would mean that we use prefixes. It's covalent bond. So we have 2 chlorine, so dichlorine oxide. And there you have it. And now we go in the opposite direction, coming up with the formulas based on their names. We'll skip A because it has polyatomic. We won't really be worried with that. So here we have boron trifluoride in B. So boron trifluoride, it's a covalent bond, very nice and easy. Tells you how many of each you have. So it's going to be 1 boron, 3 fluorines, B and F. So BF3. We'll skip C, again another polyatomic. And then D, dinitrogen tetroxide. So we have 2 N's and we have 4 O's, so N2O4. And we'll skip E because it has polyatomic again, and we're not concerned with that. And so there you have those answers. Now we can, we went through these different compounds, we went through these different types of bonds. And so now we're going to be talking about describing these bonds and talking about electronegativity and polarity. And so each atom is attributed with a specific electronegativity value. So and that value describes the attraction of the atom for its shared electrons involved in the bonds. And so it generally increases as you go from left to right on the periodic table and from the bottom to the top on the periodic table. So the upper right hand side of the periodic table are going to be the most electronegative. And actually fluorine is the most electronegative element. And so nonmetals have high electronegativities, metals have low electronegativities. And so you can see those electronegativity values here. All right, and so so with covalent bonds, we often describe these covalent bonds as being polar or nonpolar. And so what it means to be nonpolar is that there is an equal or almost equal attraction and sharing of electrons. So that means that there's almost no electronegativity difference. And so which I guess is defined as between 0.0 and 0.4 electronegativity difference. So diatomic molecules such as N2 and O2 and stuff like that are completely nonpolar because there's the same atom and there's no electronegativity difference because they are the same atoms. But you can also have other atoms that are very small differences that are considered nonpolar covalent bonds. And so you can see here some examples like chlorine and bromine. You know, there's a very small difference. Hydrogen and silicon, very small difference. And so those form nonpolar covalent bonds. We can also have polar covalent bonds where we have moderately large electronegativity differences. So between the values of 0.5 and 1.7. And so that means there's an unequal sharing of electrons. If you have, you see here oxygen and chlorine, chlorine and carbon, oxygen and sulfur, and those have large enough values to create a large enough electronegativity difference where there's unequal sharing of electrons, and they are considered polar. And so polarity is an important property based on when we talk about making solutions and when we want to mix different chemicals and see if they're going to mix together. Are they going to interact or are they going to separate? And so polarity is an important determination of that. We always say that, when we say oil doesn't mix with water, right? If you put oil with water, oil generally floats to the top, water on the bottom. And that's because oil is largely nonpolar and water is polar. And so they won't interact if they are different polarities. And so here we're going to compare the differences, and so largely it's based on the unequal and or equal sharing of electrons. So when we have H2, those electrons are going to be in the middle between those two hydrogen nuclei. So they're going to be directly in the middle because it's like a game of tug of war, and if they're going against the same exact opponent, then those electrons are going to stay in the same place. Whereas if we compare that to hydrogen and chlorine, chlorine is more electronegative. It's going to pull those electrons closer. So it's winning the tug of war. And so because of that, it's going to have a slightly negative charge compared to hydrogen. And hydrogen is going to be slightly positive because it's losing that battle. It's losing its hydrogens. Now, it's not completely lost, but they're just not shared equally. And then we can have ionic bonds. So ionic bonds are largely we have them between metals and nonmetals, and it's because we have a complete transfer of electrons because there's such an electronegativity difference. It's, if it's a tug of war, then that one that wants to be the negative charge, the one that gets the electrons, basically pulled the rope out of the other person's hand. And we see these large difference of electronegativity, so we attribute that to electronegativity difference of 1.8 or more. Now I'm not going to tell you to memorize these values or anything like that. I may ask you if it's going to be polar or non-polar, just based on their arrangements on the periodic table, or if it's going to be ionic or covalent. That should be quite evident based on if it's two metals or a metal or non-metal. I should say two non-metals or a metal and non-metal. And so, but yeah, I'm not going to make you memorize these actual values. So it's just a nice little visual aid and kind of showing you the how the electrons and the electron cloud kind of looks when you have these different types of bonds. So if you have a completely nonpolar bond, you have a very symmetrical electron distribution, like electron cloud. So it's a very symmetrical shape. Whereas if you have polar, it's pretty unsymmetrical. So you have one side that's slightly smaller, one side slightly larger. The positive side, because you're slightly losing electrons, can be slightly smaller because there's going to be a greater attraction toward the remaining electrons, and then the negative is going to be slightly larger. And then where you have ionic, you have no overlap of those electrons, but rather you are close together and bonded based on your opposite charges. And so these are just some typical compounds that you'll probably run into, and so you can see what their bonds are, what their what the type of bonds are, if they're sharing the electrons equally or if they're completely transferring, looking at their electronegativity difference, and then describing their bond types. And so then here it wants us to use the electronegativity differences to figure out what type of bonds we have. And so, we'll use that. You can use that previous table and the one in the book to figure these out. And so we'll just kind of use those values on the next slide. So when we can subtract the difference between potassium and nitrogen, we get a difference of 2.2. And again, we have a metal and potassium, a non-metal nitrogen. That should be an ionic bond. Nitrogen and oxygen, we have a difference of electronegativity of 0.5, and so that should be a polar covalent bond. Chlorine and chlorine, same exact compound, so same exact atom, and so they should have a difference of 0 electronegativity, so it's going to be completely nonpolar. And then boron and chlorine, we have a difference of 1 electronegativity, and so that's going to be polar covalent. Two nonmetals still going to be covalent, just going to be polar, just unequal sharing. which now we can bring in the idea of what's going to be the shape and the polarity of the molecule. Okay, we talked about polarity of bonds, but now we can talk about the polarity of the molecule when we have multiple bonds. And then we can describe the shapes when we have these multiple bonds. And we largely figure this out based on this method called the VSEPR method, the valence shell electron pair repulsion theory. And so this is just the electron, based on the electron groups, what is going to be the geometry around the central atom. So how are these atoms going to be arranged? And so one key thing here is you want to remember is that the atoms are going to be arranged around the central atom as far as they can from each other. And that's to create the least amount of repulsion from the electrons of the other atoms. And so whatever shape they take, whatever geometry they take of around the central atom is going to be the molecular shape. And so these are going to be three-dimensional shapes. All right, so we're not working in 2D, we're working in real dimensions, so it's going to be 3 dimensions. And so their three-dimensional shape is going to be predicted by using this VSEPR theory. And so this flowchart kind of shows you the steps involved in figuring out this molecular shape. And so first we want to write out the electron dot formula of the molecule. Then we want to arrange the non-central atoms, or electron groups, around the central atom to minimize repulsions. And then use only the atoms bonded to the central atom to determine the molecular shape. So we put all that together to get the geometry. So here if we see beryllium and beryllium chloride, we have beryllium, which disobeys the octet rule. But if we were to come up with the electron dot formula, or that electron dot structure, beryllium has 2 valence electrons, and then we have chlorine, which has 7 valence electrons. So each chlorine wants to gain 1 electron, so it's going to get 1 from the beryllium, and each chlorine gets 1 from the beryllium, fills up its octet. And beryllium would want to lose 2 electrons, so that's what we see here. Beryllium is the central atom, chlorine is the outer electrons. And so here we put the put the chlorines as far from each other as possible, and that would give that 180 degrees. And so that molecular geometry is linear. Same thing can happen if you have a molecule with double bonds. So CO2, if you figured out the electron dot structure of CO2, again, we have the double bonds from carbon to oxygen, and carbon does not have any lone pair electrons. So again, here we would have 180 degrees in linear shape. For boron fluoride, we see here that boron has 3 valence electrons. It is another one that disobeys the octet rule. And so boron has 3 valence electrons. Fluorine has 7, being in group 7. And so each fluorine needs 1 more electron. And so the boron will give the 1 electron to each fluorine. And so you put boron in the middle and fluorines around the boron. And so to minimize the repulsion, the largest angle that could be reached would be 120. And so we call that the trigonoplanar geometry. So we went over 2 examples where we have no lone pair electrons around the central atom. So now we're going to take an example where we actually do have a lone pair around the central atom. And so here we have sulfur dioxide, and sulfur has one double bond between one of the oxygens and a single bond between the other, and then is left with a lone pair around the sulfur atom. And so we call that having 3 electron groups, 2 of which are with bonds to the oxygen atoms, and then 1 lone pair. So it has the electron geometry of trigonal planar, right? Because we still have 3 groups, and the to minimize repulsion, that would bring it at 120 degrees. So that would start off with trigonal planar. But when we talk about molecular geometry, then we only pay attention to the geometry within the atoms. And so then the molecular geometry, just paying attention to the atoms themselves, would be a bent shape. And you can kind of see that in the picture on the right. So the electron groups is there, and it still provides repulsion because it's going to repel the electrons from around the oxygens. And so it keeps it away, the lone pair keeps the oxygens away from the lone pair. And so making that trigonal planar fundamental geometry if you include the electrons. But when we talk about molecular geometry, we're just concerned with the atoms. And so that would be a bent shape. And so if we were to come up with the geometry of N2O, then we will, it's probably best to describe it by actually seeing the picture. Go to the next slide. If we do N2O, we see that nitrogen is the central atom and the other one is not, and then the oxygen is a non-central atom. And so if we were to come up with the electron dot structure, each nitrogen has 5 valence electrons, and so that brings it to 10. And then oxygen has 6. And so you can go through the steps that we have followed in the previous chapters and coming up with the electron dot structure. And so you end up with nitrogen not having, the central nitrogen not having any lone pair electrons. And so because of that, then it's going to have a linear shape. It's going to be 180 degrees. And so, of course, I will post a video of working through these problems because it's a lot easier to see when it's being worked through than just on these PowerPoint slides. Next, we go to the 4 electron group. And in these cases, we'll have at least 4 areas in which will be occupied by electrons. So in this example, we'll look at CH4, which has 4 electron groups around the carbon. The carbon is a non-central. Carbon is the central atom, and so in this example, in this electron groups, the shape or the geometry around the central atom is a tetrahedral arrangement, tetrahedral shape. So basically, the angles, all the angles are equal to 109, or really 109.5. And so you have 4 bonds to the 4 bonds around the central atom, and which would create a tetrahedral geometry. If we have a 4 electron group but only have 3 bonds, then we actually have the pyramidal shape. So again, the lone pair electrons provides repulsion of the non-central atoms, but again, we only take into account the geometry of the atoms involved. And so in this case, we look at ammonia, NH3. So NH3 nitrogen has a lone pair of electrons, repels the hydrogens from that lone pair, and so we form the pyramidal shape. And so we're actually also going to conduct a lab where we are going to play around with these geometries and be able to see them and see it actually in person and see the geometry to make more sense of it. If we have a 4 electron group but only have 2 bonds and have 2 lone pairs, like in water, H2O, again, those lone pairs provide repulsion from the bonded atoms. And so in here we form a bent shape. And these are just some further examples showing the molecules and their electron dot formulas and the bonds that are involved and their shapes that they make. And you can see the different groups from there. So if we were to use the VSEPR method, we'd have to, for these examples, want to state the number of electron groups, the number of lone pairs, and then using the VSEPR theory, come up with the shapes. So for PF3, we'll just kind of go on here. So PF3 phosphorus has 5 valence electrons, and fluorine has 7. So each fluorine wants 1 extra electron. So you're going to form 3 bonds between phosphorus and fluorine, and then you're left with a lone pair around phosphorus. So you have 4 electron groups, and of those 4 groups, 1 is a lone pair. And because of that, you start off with the whole geometry as a tetrahedral, but because you don't take into account the electrons, then the molecular geometry is then pyramidal. If we have dihydrogen sulfide, then we have sulfur as our central atom, and sulfur has 6 valence electrons, which requires 2 more. Hydrogen has 1 valence electron, requires 1 more. And so you're going to have a bond between each hydrogen and sulfur, and that leaves 2 lone pairs around the sulfur. So you have 4 electron groups, 2 lone pairs. And so in that case, like H2O, it's going to be bent. You start off with the tetrahedral geometry, but then you're looking at only the atoms, then you have a bent shape. And then CCl4, carbon, has 4 valence electrons. It wants 4 more. Each chlorine wants 1 valence electron, 1 more valence electron. So carbon, and there's 4 of them, so each carbon shares 1 electron with each fluorine, and so you form 4 bonds, and you have 4 electron groups in which there's 0 lone pairs, and so that would be a tetrahedral geometry. You can have polarity within these in the geometry within the molecule. So we already went over the polarity. If there's a polar bond, how to decide if there's a polar bond. Well, just because there's polar bonds, sometimes the molecule may not be polar. It depends on if there's a equal sharing in all directions, or if there's unequal pulling in a certain direction. And so in NH3, as we have drawn, we have the 1 lone pair of electrons, and then we have these 3 polar bonds between the nitrogen and the hydrogen. And because there's 3 polar bonds between nitrogen and hydrogen, and and they're not pulling, their dipoles are not able to cancel each other out. If there was 4 hydrogens, then their geometry would be such that it would cancel out. But because there's only 3 of them, then they do not. And it's kind of hard to visualize. I understand that, and you probably kind of have to see the models and be able to really identify that. Um, Nonpolar molecules, they have they can either have nonpolar bonds, but they can also have polar bonds in which they have symmetrical. Uh, uh, they have pulling of these polar bonds, and it's a symmetrical pulling, so it cancels each other out. So in the example of carbon and oxygen and CO2, they are pulling in opposite directions, but because carbon's being pulled in the opposite directions, that they're canceling each other out. And so that happens with the uh, all of these examples, even looking at carbon tetrachloride. And so that kind of takes kind of practice getting looking at that. And I don't think I'll be asking you questions like that on the quiz. I think that would be a little bit too advanced and difficult to figure out. And so we'll just skip over these next few slides looking at determining molecular polarity. So although it is important in discussing, because if we have polar molecules, as I had discussed before, polar molecules don't really mix with nonpolar molecules. That's the reasoning behind the oil not mixing with water. Water, like is showing here, is polar, whereas oil is nonpolar. But we won't really go into the idea of determining if it's polar or not. So we'll continue skipping over slides. But we do want to talk about what happens if you have these polar molecules and the forces between the different molecules with these forces. And so we discussed before, ionic compounds have ionic bonds, and so there are large, strong charges that are attracting of opposite charges. So all positive charges will be attracted to negative charges, and that's what keeps these ions together. And so ionic bonds have ionic charges, which are very strong charges. Dipole-dipole attraction. So if you have polarity within your molecule, it's called a dipole. And so when you have multiple molecules with dipoles, they form dipole-dipole interactions. So if you have one molecule that has a dipole and another molecule has a dipole, then those dipoles will be attracted to one another. And the form is strong of a dipole interaction is called hydrogen bonding. And they're not actual real bonds, but they are these dipole interactions that are formed between the large polarities created between the highly electronegative elements such as fluorine, oxygen, and nitrogen when they're bonded to hydrogen. And so you have these high polarities based on these large electronegativity differences, so you have strong dipoles. And when you have these different atoms that have these strong dipoles, they interact and form strong dipole bonds. And so you see that here you have an example of dipole-dipole interactions where you have just a polar bonds created, in this case bromine and chlorine on the bottom part. And so bromine is slightly less negative, electronegative than chlorine. So chlorine is slightly positive, bromine slightly chlorine slightly negative, bromine slightly positive. So the slightly negative of chlorine can be interact with the slightly positive of a bromine that's involved in another molecule. The same thing is done with hydrogen bonds. The only difference is that you have those highly electronegative elements such as fluorine, oxygen, or nitrogen with hydrogen. So the highly electronegative fluorine, which is going to be slightly negative, is going to be attracted to the slightly positive hydrogen, of another molecule. We can also have weak attractions called dispersion forces that are attractive forces between nonpolar molecules that can cause temporary dipoles when their electrons are not distributed equally. And so you can have a temporary shift in electrons. So even though if you can have, in this case, two fluorines bonded together, which would be completely nonpolar, if something influenced one of them to have a slightly positive charge, then the other one would have a slightly negative charge, and then that would create a, basically a chain reaction to have this temporary shift in the electrons. But then, it would eventually go back to normal. But again, those dispersion forces are weak. And so here you can kind of just see the differences in their strengths. And so dispersion forces are the weakest, then dipole-dipole, then hydrogen bonds, which are a special type of dipole-dipole, and then ionic bonds. And so these are attractive forces keeping parts of different atoms and molecules attracted to one another. And so that is related to some of their physical properties. Because of their strengths, then they'll have different properties. So in the case of ionic compounds, there's a great strength in those forces. It's going to keep those things together. It's going to take a lot to break them apart. And so because of that, it's going to be they're going to have very high melting points. As we described before, ionic compounds such as salt have very high melting points because there's such a strong attraction between sodium and chlorine ions. Hydrogen bonds are the next strongest, and so they require a lot of energy and more energy than other dipole attractions. And dispersion forces are generally pretty weak. And so they require very little energy to change their physical states. And so that's why you kind of see, fluorine and chlorine and things like that have, there's not very much attraction to each other. And so they're usually found in the gaseous state. And so you can kind of see that here, their melting points and their different attractive forces. And so the more strength and the stronger the attractive forces, the higher their melting points. One other thing to say about dispersion forces often correlate with molecular weight. And so the greater the molecular weight, usually the more dispersion forces. And so that's why you can kind of see chlorine has a higher boiling point or melting point than fluorine, because chlorine weighs more, so there's more dispersion forces there. And that's generally how it can go. It doesn't always prove to be true, but that's the more often than not. So here we have to identify the type of attractive forces between each. So if we have nitrogen and chlorines, so nitrogen trichloride, we would have dipole-dipole interactions. So there's going to be there's going to be a difference in electronegativities, creating dipoles or polarity. But because hydrogen is not involved, it's going to be dipole-dipole interactions. Hydrogen and oxygen, again, we have polar bonds, so it's going to be dipole interactions, but because it's hydrogen with oxygen, it is considered a hydrogen bond. Bromine, it's going to be nonpolar, so that's going to be dispersion. KCl, we have a metal with a nonmetal, ionic bonds, ionic attractive forces. And nitrogen and hydrogen, we have polarity in their bonds, but so it would be dipole-dipole, but because it's nitrogen with hydrogen, that would be a specific type of dipole, which is called hydrogen bonds. So you can see the answers here. And so that brings us to the conclusion of Chapter 5. And so Chapter 5 brings us, that is going to last for 2 weeks. So you're not really responsible for any lectures until February 18th. The quiz on Chapter 5 is going to be on February 16th, in which also homework assignment 3, which is based on chapter 5, is due on February 16th. And chapter 5 is also the last chapter that you're responsible for in terms of the midterm, which is going to be on February 23rd. So next week I'll post a YouTube video going over problems related to much of this information. And then I will the following week I'll probably post a video that goes and reviews over much of the material that will be on the midterms, so chapters 1 through 5. So there won't be a PowerPoint lecture posted for next week because this lecture goes for the 2 weeks.